Welcome, everybody, to the Fluids Notes. A fluid is any material that can flow, like a liquid or a gas. In this unit, we analyze fluids that are not in motion and look at pressure as it depends on depth. We look at Pascal's principle, the idea that pressure at any depth in a fluid is the same at every point that's at that depth. We'll look at buoyancy, the force that a fluid exerts on objects within it. Then we'll look at fluids that are in motion. We'll look at how conservation of mass affects the flow of fluid and how conservation of energy affects the flow of fluid. But before we do any of that, we have to talk about the idea of density. In physics, density gets the symbol of the Greek letter rho. It looks like a lowercase p, but it's a little curvier than that. Density, as you know, is mass divided by volume. Therefore, density times volume is mass. The density of a material is one of the ways we can tell what that material is. There's only one density that you really should know, and that's the density of water. As you can see on the left, the density of water is a kilogram per liter, which is also 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. On the top right, that's the density of the core of the sun, about 150 times denser than water. Mercury is about 13.5 times as dense as water, and wood on the bottom is less dense than water. So, a quick practice problem. What is the mass of a solid iron wrecking ball with an 18 centimeter radius? Well, we know the density of iron. You can look it up. It's just almost 8 times as dense as water. The volume of a sphere is 4/3 pi r cubed. I'm going to go ahead and solve this one, but do follow along. Density is mass divided by volume. So mass is density times volume. Volume is 4/3 pi r cubed, so we use the density of iron times the volume of the wrecking ball for a mass of 190 kilograms. You've heard me compare the density of materials to the density of water. For example, the sun is 150 times as dense as water in its core. Language like that is the language of specific gravity. Specific gravity is the ratio of a substance's density to the density of water. Specific gravity is a scalar. It has no units. It just is. The specific gravity of Mercury would be 13.5. Since the density of water is 1,000 kilograms per cubic meter, the specific gravity of any material is its density in kilograms per cubic meter divided by 1,000. Which means the specific gravity of a material is also numerically equivalent to its density in grams per cubic centimeter. Water has a specific gravity of 1. Wood has a specific gravity of 0.75. What do you think your specific gravity is? How could you change your specific gravity? Back in 2017, Hurricane Harvey rained 27 trillion gallons of water on the city of Houston. 27 trillion gallons written out is a really, really big number. The density of water is 1,000 kilograms per cubic meter. What's the mass of the rain that fell in Hurricane Harvey on the city of Houston? If YouTube allows comments on this video, you should put your answer there. There, scaled to the size of downtown Houston, is a single raindrop, the size of the rain that fell during Hurricane Harvey. That's a lot of rain. Any fluid at rest exerts forces on surfaces within the fluid. It can only exert forces perpendicular to the surface. Fluids only push. The term pressure refers to the force per unit area. So we say pressure is force per area. So force is pressure times area. Here those are in a bigger font size if you didn't write them down. The units for pressure are newtons per square meter, which we call pascals. You've definitely felt that when you swim lower in a swimming pool, the water is pushing harder against your ears. What you're feeling is called the gauge pressure, and that's the pressure due to the weight of the fluid above you. That's also called hydrostatic pressure, meaning a fluid that's at rest. Here's a quick derivation of how we calculate gauge pressure. You don't need to write this down, but the bit at the end is going to be useful. Near Earth's surface, it's pretty easy to determine the pressure exerted by a static fluid because any element of it is in equilibrium. It's not moving around on us. So, in this volume of fluid, I'm going to specifically look at that small piece on the inside of height h. At that point, the force at the bottom of it, the force due to the fluid pressure is equal to the weight of the fluid column. Well, weight is mass times gravity, and mass is density times volume, and volume is area times height. So we put it all together and say that the weight is the gauge pressure times the area. That term sort of nestled in there is density times gravity times height. Here it is in a bigger font size, if you'd like to write it down, which you should. Gauge pressure is density times gravity times height. Or you might look at it as depth in the fluid. Yesterday's interactive lab had you graphing pressure versus depth. A lot of you were great at recognizing that the slope had something to do with the density of water, but this specifically is what the slope had to do with the density of water. If we graph density on a y-axis and height on an x-axis, that rho g term is the slope. So what you found was the density of water times gravity. This might help on tonight's homework. The surface of the water in a storage tank is 30 meters above a kitchen faucet. Can you calculate the gauge pressure at the faucet knowing that the density of water is 1,000 kilograms per cubic meter? Well, density is 1,000 kilograms per cubic meter. Gravity is 9.8 meters per second squared. And the difference in height is 30 meters. So the gauge pressure is about 2.9 atmospheres, or 2.9 times 10 to the 5th pascals. That term that I used, atmospheres, that might be familiar to you if you took chemistry. The air itself exerts pressure. Air is, after all, a fluid that flows. If there's additional force exerting pressure at the surface of a liquid, such as the pressure from the atmosphere, then the total pressure within the liquid is the sum of the surface pressure and the gauge pressure. That sum of pressures is called the absolute pressure. So, the total pressure at any depth, due to the weight of the fluid and a force on the surface, is the sum of the atmospheric pressure and the gauge pressure, called the absolute pressure. 1 atmosphere of pressure is about 10 to the 5th pascals. How far would you need to swim underwater to reach 2 atmospheres of pressure? That is, how far under the surface would you need to swim to have 1 atmosphere of pressure from the atmosphere and an atmosphere of pressure from the water? Well, we can algebra that one out. And find that it's about 10 meters. Probably an easier way of looking at this problem is saying, how far underwater would you need to swim to have 1 extra atmosphere, that is, 10 to the 5th extra pascals of pressure? Now, as I said in the introduction, Blaise Pascal had this idea that external pressure applied to an incompressible fluid, like water, is transmitted throughout the entire fluid. Squeezing on one part of a fluid squeezes on all parts of the fluid. So here is a vaguely U-shaped container. It exists in 3 dimensions, but you can only see it in these 2. When a force is applied to one of those movable yellow pistons, watch it, it's going to push down. When a force is applied, extra pressure is applied everywhere in the fluid. What that means is that the pressure on the left, that's the force on the left per area on the left, equals the force on the right per area on the right. The pressure on the left equals the pressure on the right. An important consequence of Pascal's principle is that the pressure at any depth in that fluid is the same regardless of whether we're considering the left side of the tube or the right side of the tube. If you just pick a height partway up either side, the pressure on the left end of the tube will equal the pressure on the right side of the tube at the same height from the ground. This is how a hydraulic jack works. A small force becomes a big force. The force supplied by the right piston in our previous example is proportional to its area. So let's take a look at that again. If a small force is applied to the left piston, a big force is applied by the right piston. A small force on the left yields a big force on the right. The force per area is the same. Now, I know what you're thinking. Doesn't that violate conservation of energy? You can't get out more force than you put in, right? The piston on the left moved a greater distance than the piston on the right. The same amount of work is done on either side. Conservation of energy has to work. This is why my daughter can use a hydraulic jack to lift my truck, even though she couldn't lift it with her bare hands quite yet. She can definitely use a hydraulic jack. Now, every pump of a hydraulic jack moves the handle about 3 feet. Every pump raises my truck about ½ an inch. Pascal's principle is also useful if you're trying to punk your friends. Here is a jug full of water. The spout's area is about 5 square centimeters, and the base's area is about 500 square centimeters. If you were to shove a stopper into the top of that jug with 10 newtons of force, how much force would be applied to the base? Well, we can apply Pascal's principle and say the force per area on top equals the force per area on the bottom, so that the ratio of the forces is the same as the ratio of the areas. A 10 Newton force applied to the top of the jug becomes a 1,000 Newton force apply to the bottom of the jug. If you slap like a glass bottle of IBC root beer or something, and it's full, you apply a small force to the small area of the top. If you do it just right, you can rocket the bottom off with a large force because it has a larger area. Don't try this at home. Try it at your friend's house.